Today we will look into another controller, which is proportional derivative, or famously known as PD controller. P for proportional, D for derivative controller. In the previous class, we discussed PI controller. PI refers to proportional and integral controller. What is the purpose of PI controller? Can someone describe what is the purpose of PI controller? Anyone?
To improve the steady state error equal to 0.
So PI controller used to improve steady state error. Okay, usually we want steady state error to be 0. Then we have to increase the system type. And also we want to maintain the transient response. That is PI controller. Today, we move into PD controller. PD controller is in opposite. It's used to improve transient response and maintain the steady state error. Later, we can combine PID, in which we can improve steady state error and also improve transient response. We go step by step, PI, then today PD. How to implement PD controller? PD controller is performed by adding a single 0 to the forward path. What we do, we will add 1 0. Remember, for PI, we add 1 pole at origin and 1 0 near to the origin. PI, we have 1 pole, 1 0. But PD, we add only 1 0, a single 0. Okay? The location will have to be determined. We need to do calculation in order to determine the location of the 0 that we want to add. Okay? So a proper selection of the 0 can improve the system transient response. So the location will be based on desired response. Let's say we want overshoot 10%, we want settling time 1 second. So that will be used to locate the new 0 that will be added. Okay? So the transfer function of PD, we call GPD, is KP proportional plus KDS. Okay? For PD, we multiply gain with S. Remember yesterday for PI, we divide by S. Okay? And this can be also written as, if I take out KD, is S plus KP over KD. Can be also written as K S plus Z. Z is the 0 that we will add into the system in order to achieve desired response. So this is PD. The implementation is here. Okay, you can see that it is it can be written in two different blocks, two separate blocks. First one KP. KP here is similar to KI. sorry, K1 here similar to KP, KD is K2S. Okay, just we put K1, K2. Then some is used to add both signal from both blocks. So it will be the same. It will be K1 plus K2S. Okay, is KP plus KDS. This is PD controller. Next, we want to show what happens if we add a 0 into an original system. This is the effect of adding 0. Let's say this is the original system, the root locus of the original system. They have three poles, -1, -2, -5. And this is the root locus. And zeta 0.4, we get this value. This is the dominant -0.9, J 2.1, K equal to 23. The next diagram here or picture here showing block a new root locus. If we add 0, here we add at -2. See, we add -2. Root locus will be like this, because now asymptote become only 2. 3 minus 2 become 3 minus 1 become 2. The angle will be 90 degrees. So this is what we get. And if this at the same zeta 0.4, we get dominant pole -3 plus J6. We compare here -0.9. Similarly, we add another one just to test at -3. This before -2, we add -3. It's like this. This is the dominant pole. Then we add at -4. This is the dominant pole. Okay. So from these investigations, we can see that if we add a 0 into the original system, the dominant pole move toward more far from the origin. Okay, you see, initially -0.9 become -3 or -2.7 or -1.8. Okay, remember TS 4 over zeta omega n. When omega n is increased, then when zeta omega n is big, then TS is low, is faster. So first we can see that when we add 0, system will become faster as compared to the original system, because it moves more far toward the far from the origin. Next, we can see that the imaginary part, initially J 2.1, now J 6.8, 5.8, 4.2. Again, TP pi over omega d, we can see that when we add 0, omega d increase. Therefore, TP also reduce, small TP. Reduced TP means system become faster. So in conclusion, adding 0, system will have more negative real and large imaginary part and become a faster response. That is the good thing of PD. We add 0, system become faster. The next question is where to put the 0. Okay, this is just a test. We put -2, -3, -4. But in general, adding 0 will improve the transient response, will make the system faster. But the exact location will be dependent on the desired specification. This is the responses. When we add 0, this is the initial one, is improved. Okay? It's faster, settling time fast, small settling time, small TP, so it's very much faster than the original system. Okay, let's do an example. As I mentioned just now, the important issue here is how can we calculate the location of 0. I will show how to calculate by solving, by going into this example. Okay, if hopefully by at the end of this example, you know how to calculate or how to find the location of 0. Okay. Before that, I would like to remind that PD controller is very important. Surely it will be asked in the final exam. Okay, because final exam, normally we ask PD or PID. In either case, PD is important because PID is basically PI plus PD. And PI is, we discussed yesterday, is easy, no need calculation. Then PD become very important. Okay. Okay, given the system, this is the original system. Design a PD controller to yield. Yield means to have or to obtain or to achieve 60% overshoot. We want system 60% overshoot with a threefold. Threefold means 3 times. Fold here means times. 3 times reduction. We want to reduce settling time by 3 times. If initially 3 seconds, we want to be 1 second. If 6 seconds, we want to reduce 3 times, become 2 seconds. So it will be depend on the original system. Therefore, we need to first analyze the original system. And again, I reminded this one many times. In here, we will use root locus to analyze and to design PD controller. Okay, let's see the original system. Normally, this is given to you in the exam, the original root locus. See, we have pole at -0, -4, and -6. Okay. We want 60% overshoot. Then here we can calculate zeta. Zeta is 0.504. A graph will be given to you, then you can calculate zeta. You can take zeta from the graph, is 0.504. This is the root locus, and we can make a zeta line, 0.504. And this is the dominant pole. Okay, this is the dominant pole of the system. I will show here. Dominant pole. S equal to minus 1.205 plus minus J 2.067. Now we want to analyze the original system. I want you to find TS, settling time. Remember, we have to design based on the original settling time. We want peak time. And we want you to find error. Error to RAM input. Okay. You see, this is a type 1 system. If we calculate error based on unit step input, then surely it will be 0 because this is type 1 system. If RAM input, then you can get value, not 0. Okay, now find TS, TP, and error to a RAM input. The value here is given, including K, K43.35. We have done this yesterday. Okay, now find TS, TP, and error for the original system. What is the value of TP? Anyone can have TP, TS? What is the value of TS and TP? One 1.5 TP pi over 2.064 is 1.52 second. TS 4 over 1.205 is 3.32 second. Now find error. Error for RAM input is equal to 1 over KV. Okay, remember we have KV, KP, KA. For RAM input, 1 over KV. And the formula for KV is limit S0 SGS. The limit S to 0 S, our GS is this, is 1, is K 43.35 divided by S plus 4, 6. Its S can be cancelled out. Then we get 43.35 over 24 kV. Therefore, error is 24 over 43.35. So 1 over kV. 0.55. That is error. So error not 0. Any question here? Is next question, is second order approximation valid? Is second order approximation valid? Yes or no? Thank you, Najiha. Is valid because this is the third pole. The third pole is as negative 7.59. Then 759 divided by 1.205 is greater than 5. Then this is valid. Okay, because the dominant pole, because the third pole is far 5 times more than the dominant pole. Is shown here the same. Okay, now we want to move into designing PD controller. Our original TS is 3.32 seconds. Okay, obtained from here. And remember, our objective is to have 3-4 reduction in the settling time. The objective is to have 3-4 reduction. That means 3-4 meaning 3 times. So desired TS is equal to 3.32. We divide by 3. It's 1.11. Okay, to be exact, 1.107 seconds. We want our system to improve the transient response, to improve the settling time from 3.32 seconds into 1.107 seconds. How can we design a PD controller to achieve this new desired settling time? And we want the other one overshoot at 16%. Overshoot means we maintain from here because design a PD controller to use 16% overshoot and settling time reduced 3 times. So 16% overshoot meaning zeta is 0.504. Okay, the next task is to find a new desired closed loop pole. We need to find a new closed loop pole. We want to change, not this one anymore. This is the original one, minus 1.205. Now we want a new one because we want new TS. Okay. TS is 4 over zeta omega n. And we want equal to 1.107. This is the new one. Therefore, zeta omega n is 4 over 1.107. That is zeta omega n. And we want also zeta 0.504. Then surely we can obtain omega n. Therefore, omega n is 4 over 1.107 and then 0.507 is equal to I don't have the value here. wait. Actually, no need to find omega n here. I can just take this, because this will be our new one, zeta omega n, which is equal to 3.613. This is new zeta omega n. In order to achieve TS 1.107. Right? So if I can draw the dominant pole here, it is here, the new dominant pole. The value here is minus 3.613. And if I draw the zeta line, zeta here is 0.504. Next, we need to find this value, the J value here. J omega D. Many ways to find. We can find omega n as just now. We have zeta omega n 3.613. We can find omega n 3.613 divided by 0.504. Okay, I don't have the value. You can calculate. Then omega D is omega n 1 minus zeta squared. This is the formula for omega D. If you calculate, it will be 6.193. So this is equal to J 6.193. Or if you do not want to use this, you can find the angle here, theta. Okay, remember cos theta equal to 0.504. Then if you know theta, you can also use trigonometry to find the value on the y-axis. If you know theta. Many ways to calculate omega D. Zeta omega n can be obtained from Ts. Therefore, the desired closed loop pole is S equal to minus 3.613 plus minus J 6.193. Okay. So we need to find the desired closed loop pole. Desired closed loop pole to achieve desired response. In this case, to achieve settling time reduced by 3 times. Any question up to here? Any question? No. If not, we will move. Okay, let's move. Okay, now come to the last part in which we need to find the location of a zero. Okay. So we, as we know that we want to add a controller. This is the original system. We want to add GPD. Okay, in which GPD is S plus Z. Okay, K S plus Z. We want to find Z, meaning that we add 1, 0 into the system. Our desired pole is as calculated before, plus minus J 6.193. Okay, now we want to plot on the S plane. We have the original system, the original pole here, 0, minus 4, minus 6. This is the desired closed loop pole. Minus 3.613 J 6.19. We say that by adding PD controller, we add 1, 0. So we add 1, 0. 0 here. We do not know the exact location. We want to find 0, the location, but initially we just put 0 at any place on the real axis. Okay? So the next is to find 0. The location of 0 can be obtained by using the property of root locus. We use property. That means in this case we will use the angle. Okay. So first I need to take all the angle from pole and from 0. Let's say here theta 1, theta 2, theta 3, and theta 4. The property that we mentioned here is total angle from the pole minus total angle from the 0 is equal to 180 degrees. Or plus minus 180 degrees, both the same. Okay. In fact, if you change 0 minus pole, also give the same answer. Okay, because 180 degrees can be positive, can be negative. So I use angle from pole minus angle from 0 equal to 180 degrees. By looking into the root locus here, the diagram here, we can say that theta 1 plus theta 2 plus theta 3 minus theta 4 equal to 180 degrees. Okay, so of course, the next task is to calculate all the angles. Theta 1, theta 2, theta 3. Therefore, after that, we can calculate for theta 4. So what is the value for theta 1? Anyone can calculate? Value for theta 1. We know 6.193 here. This is 3.613. Then can calculate theta 1, theta 2, theta 3. Theta 1 is 120 degrees. 120.2 or 0.3 degrees. Right? Is it correct? Please calculate for theta 2 and also theta 3. I don't have the value. Please give me the value, the answer. Anyone? Theta 2? So you can find theta 2. I'm not sure 86. 86.4. I'm not sure. I have to check. And theta 3 also. Then you can calculate for theta 4. Theta 4 is theta 1 plus theta 2 plus theta 3 minus 180 degrees. The answer for theta 4 is 95.6 degrees. Okay, theta 86.4, 72.1. Please check, I'm not sure, but theta 4 is correct, 95.6. 68.9. You have to check, eh? Okay, I think you have to be more proactive. Otherwise, I'm not sure whether you are following the class, you are not, and you did not follow. I'm not sure. Okay, that's why actually I'm asking. The way I teach is I hope that the student will follow, will do the same, will do in the class. Okay? Otherwise, I can also give a full note. I can give the same as the book. I can just read the slide, no problem. Okay? But I think by doing the activities, it will be it will increase your understanding rather than just write or read the notes. Okay, I can give the value is in the book. Okay, but I purposely did not take from the book. Okay? I want to do it. I want you together with me do the same. You follow the lecture. But it seems that I'm not sure whether you're doing it or not. Okay? But I have no choice. I have to go on. But if you think that giving the full note is better, then it will be easier for me. I can just read the notes, okay, without writing. Not easy also to write. The theta 4 is 95.6. Then we need to locate the position of the 0. Okay. This is the dominant pole, minus 3.613, J 6.193. So now we know that theta 4, which is the theta or the angle for the 0, is 95.6 degrees. So we have to decide whether 0 is here or here. That means to the left or to the right of the dominant pole based on the angle. Okay? As it is more than 90 degrees, because if the 0 is here, then it will be 90 degrees. But because it is more than 90 degrees, surely it is on the right, to the right of the dominant pole. It will be here, Z. Okay? Although initially I put here. Okay, this is just a guess, but the exact location is here, is on the right of the dominant pole, and the angle is 95.6 degrees. Okay, so you need to locate Z based on the angle. Now we want to find the exact location of Z. So we know this is 95.6. Here is 84.6 degree, 84.4 degrees. So we have like this, 84.4 degrees. And here is 6.193. Here is X. The distance here, X. You can calculate X. X is about 0.6. based on tangent of 84.4, 6.193 over x. If you calculate x, will be about 0.6. So the distance here is 0.6. Here we know is minus 3.613. So here should be minus 3. So the location of z here is minus 3. Okay, please, if you could not understand, please redo it. Redo at home. Z here is minus 3. Therefore, GPD S is S plus 3. And as we know, it should be with K. Ks plus 3. How can we get K? K is obtained by using the same technique that we used before, but now with an added 0. So is here minus 3.613, J 6.193. We have pole at 0, pole at minus 4, pole at minus 6, and 0 at minus 3. Then we can calculate for K, L1, L2, L3, L4, and K is L1, L2, L4 divided by L3. Please also do this and you will get the result as 47.45. Okay. Therefore, the final transfer function for PD is 47.45 S plus 3. So we have to obtain G transfer function up to here. Okay. Of course, the most important one is to find the location of Z. Is shown here also. Z equal to 3. Actually, I've shown in the description, in the calculation just now. This is the new root locus. You can see that pole at minus 0 and minus 3. And this is the new dominant pole as we desired. And this is the new K, 47.45. And this is the complete transfer function. This is not GPD. This is G. This should be G, PDS, and G. I missed G. Okay, so it's 47.65 S plus 3. This is from PD. This is the original one because we add, because we put in series. This is 47.65 S plus 3. Here 1 over S, S plus 4, S plus 6. And this is the new root locus. And if we plot the response, will be like this. You can see the uncompensated one, meaning the one without controller, is just now we get 3.1 something, 3.1, 3.32 settling time. Now we can see that it is faster, settling time at 1.107. Okay, it settled down faster than the original system. So that is PD controller. Please revise if you could not understand. We will do a few more examples in the next class. Any question?
Doctor.
Yeah.
From the slide yang tadi, how you get x equal to 0.6?
We know value here. We
Yes.
know angle here. Then you can use tangent. Right?
Oh, okay. Right.
Then you get 0.6.
Okay, Doctor, thank you.
Okay. Any other question?